website was down yesterday, so it wasn't just me. Anyway, we talked about yesterday how area for volume, let's see if we can get there. There we go. Ooh, that's snazzy. We're not quite there yet. How area is important. Area between curves is what we talked about in section 6.1. And area is also helpful for volume in that when we are trying to, in like simple geometric shapes, when we're trying to find the volume of a figure, we can think about the area of the base times the depth or times the height. Area of the base times the depth or times the height. That works for a rectangular solid. That also works for, you put in the rectangle. That also works for a cylinder. Area of the base, which is pi r squared times the height or the depth. In order to get volume, we need area times depth. Almost all, well, it is always, but sometimes it's a little bit harder than others, like a sphere. How does that work? 4/3 pi r cubed is volume. We need area of the base times the depth. Now, when we looked at yesterday those student projects, we'll actually have an illustration with these ones. Give me 1 second. Let's come over here and see what this has brought up. Let's start with this. Okay, let's get a lighter color because that's a little bit rough. That's kind of ugly. That's kind of rough too. We'll just do that. Okay. This is being used to try to find the volume of a sphere. You guys see the sphere? Let's do another obvious color. Is there an obvious color underneath? The blue. There we go. We're trying to find the volume of the shape underneath, which is a sphere. However, without the geometric formula, remember kiddos, we're just trying to approximate right now with cylinders. Question. Is this a finite number of cylinders, or we could call it disks, that are being put together to approximate the volume of the sphere? Yes or no? Yes. Now, if I was to start with just one, how close is that approximation? Not so good. If I split it into 2, or 3, or 4, or 5, or if I keep on splitting it, what's happening as I am making the depth of the cylinders smaller? It's converging, or it's getting closer and closer and closer to the actual volume I'm trying to find. Now, wouldn't it be nice if I could have the number of disks approach infinity, aka what's going to happen to the depth as I get infinitely more, or I try to approach an infinite number of disks contained? The depth is going to approach 0. Question, when else in calculus have we had the depth, or maybe I could say something like the base? When else in calculus have we tried to make the depth, or maybe in this case, since we're talking about area, the base approach 0? Area under the curve, and what solves for area under the curve? Integration. Integration says we're going to fit in infinitely many rectangles in a finite space. We're going to have the base, which is our dx, approach 0, and we're going to accumulate f of x, which is the height, times dx, which is the base. Accumulate height by base as the bases approach 0, and we're going to add them all together. That's what integration does. So how do we use that idea of integration? Let's close that one. To help us with volumes, we say, okay, instead of accumulating base times height, we're going to be accumulating volumes, thinking about the most basic ones. What the volume would be for each of these? Well, the volume would be the area of the base. Guys, if I was to spin this, what is the area of the base of these cross sections or these slices? Circles, yeah, pi r squared. So I'm going to use pi r squared. How am I going to get depth? I'm going to multiply by dx or dy, depending on the orientation. This one right here, question, if it was oriented this way with an x and a y axis, would this depth be dx or dy? Dy, because it's vertical. We saw that yesterday in our forever card, which is chilling over here somewhere. Where is he? Here we go. When we're slicing perpendicular to the y-axis, when our cross-sections are perpendicular to the y-axis, the depth will always be dy, and that's what this one is. But if it was to be turned on end, let's see if I can get it there. If it was to go this way, question, what would the depth be of my slices? Now it'd be dx, because it would be oriented the other way, right? So we're going to set up our integral based on whether the depth is dx or whether the depth is dy. And then we are going to say, hey, how do you find volume? It's the area of the base times the depth, or the area formula, which is our forever card, the area formula of the cross sections in terms of x or in terms of y times the differential. That's forever number 47. We got it? Okay. So let's go ahead and say, sweet, can we use it? And here are a couple examples that we're going to try to use it on. Now, I know this is a little weird. Let me actually try to show you an illustration of this real fast. It's a little hard since it's three-dimensional all of a sudden. Can I use, no, not that one. Let's use this one. Oh, yeah, the 6-2A. Kiddos, if I was to spin this around, and if I was to not have it popping out in the third dimension, if I was just to try to have it in the second dimension, just pretend this is y and this is x, what kind of problem does this look like? Area between curves, right? But as soon as I put in another axis, what's popping up out of that area between curves? Cross sections. And can anyone tell what the cross-sectional slice would be if I was to take a knife and slice it right here and separate? What would it look like? A triangle. How about now? A semicircle, right? How about right now? A circle. How about now? That one's weird. Hey, that looks a lot like that one though, right? Huh. So then coming on back. How about this one? Rectangle. Weird, but true. If I was to slice it, right here, it'd go over, down, down, over. That would be a rectangle. Can I zoom in? Oh, sad day. There's no way to zoom in this one. Plain sauce. So anyway, that's what's going on in the sense of, if you guys were to notice, technically, before the square, before the rectangle, shave away the third dimension. What's true about each of these bases, in a sense? Each of these bases of these shapes. What's true? They're flat bases, and they're also coming out of the exact same two functions. The exact same two area between curves. So let me go ahead and let's make that one a green one, and then let's make this one a red one. Let's make it blue. Okay. X squared minus 1. Isn't that going to be a parabola? Question. Do you see a parabola? Me too. Do you see a parabola on this one? I do also. Now the green one. What's that one going to be? A line. Do you see a line? I do. Do you see a line of this one? I do. So if you guys notice, we actually have to use the idea of area between curves in order to help us with this now idea of volume. Now, as we're looking at each of these shapes, the area between the curves would be, in a sense, this bottom region from which the slices are popping up out of. Does that kind of make sense, kiddos? The area between curves, that's the x and the y. If you notice down here, we have our y-axis, we have our x-axis, our x and our y. If we were to shave away the third dimension, then we would have, that shouldn't be shaded right there. There we go. We would have area between curves. But what is, in a sense, popping up out of the area between curves? Slices. What kinds of slices? Well, in the first one, what kind of slice is it? Square. In the second one, what kind of slice is it? Rectangle. We saw from our forever card that to find the volume, wait a minute, can you guys tell? Is this going to be a dx or is this going to be a dy? Can you see? Isn't that a dx? Because it's perpendicular to the x-axis. How about this one? Is this one going to be a dx or a dy? Dx, same thing. Because if you notice, isn't it perpendicular to the x-axis? Okay. So we're slicing perpendicular to the x-axis. I know that was kind of gross and ugly, but we have the idea. We're trying to get high day. Okay, so we're doing this in terms of x. So we're thinking about the volume formula in terms of x. We're going to do some sort of x1 to some sort of x2, an area formula in terms of x with a dx. And the integral is going to make those slices infinitesimally thin so that there's not as much air. And it's going to make the accumulation of all of those slices, as the slices get thinner and thinner and thinner, converge to the actual volume. Integration does all that work for us. Now, question, can you guys tell, for the squares one, let's zoom in on him. We know what formula we're trying to plug in. What are my x bounds? Wait, why am I choosing these 2 points? Aren't they intersections? So it intersects at 2 and it intersects at -1. Question, should I be able to trust that you guys can find the intersections and that they end up being at -1 and 2? Yes, it's a quadratic, get all to one side factor. Okay, so my bounds are going to be from -1 to 2 of area of who? Well, what's my slice, guys? It's a square. So I'm going to, now pause, I'm going to somehow need to use s squared. Wait, s squared. Oh yeah, area of a square. With somehow a dx at the end. But question, how do I get s squared in terms of x? How do I get s squared in terms of x? If I'm talking about s squared, this is a square, right? Isn't that the exact same thing as this? Okay, so hold on, let's not focus on the up, let's focus on the down. What do you guys notice about the base of the square? What's on top? What's on the top of the base of the square? A point on the green line. What's on the bottom? Wait, top and bottom? When have we done top and bottom? Area between curves, right? Oh. So what can I say the side of the square is? S equals top minus bottom, and what's the top in this one? I don't think it's 0. Look at the top. Isn't this the green curve? The top is the green curve. Remember? Imagine, oh, did I already close it? That'd be really sad if I did. I did close it. Okay, never mind. Give me back. And the one that I showed you where I switched it and I oriented it, you were able to see the area between curves. This square is popping up out of this top minus bottom area between curves region. And so wherever the square is, down here the top minus bottom is really small. So the square is really small. Over here the top minus bottom is really big. The square is really big. The square is determined, the slice is determined on the top minus the bottom. So how do I get the s squared? I say who is the top, and the top is x plus 1. Minus who is the bottom? X squared minus 1. Side squared dx. Side squared dx. So here's my side, and I need to square him. So we think about the area formula of a square, it's side squared. And we go up to the picture and say, who is the side? The side is going to be the top minus the bottom. What's going to change in the next picture? Well, not the bounds, because the bounds are the exact same since we're going between the exact same region, which is -1 to 2. The area formula, though, is now going to be base times height with a dx. What do we know about the base of our rectangle? It's top minus bottom again, right? So I can say the base of my rectangle is going to equal top minus bottom. Now that's a struggle. I have the base. How on earth do we get the height? What do they tell us in the problem? And they always have to tell us because without telling us the height, we're lost. The height is 1. So all we have to do is say, all right, cool, top minus bottom. So I'm going to have my x plus 1 minus my x squared minus 1. Base times height. Base times height. Base is going to be top bottom. Height, as they told me in the problem, is 1. What if they said height was 2? What would I change? Yeah, the 1 to 2. If they said the height was 10, I change it to 10. What if they said the height is 2 times the base? Well, I do the base and then 2 times and the base again, or maybe 2 times base squared. Whatever clue they tell me about the height, I plug into the h spot. The base was found from top minus bottom again. Kiddos, why am I not going to solve these 2 integrals? Because you should know how to solve a definite integral once it is set up. Are these set up and ready to be solved? The answer is yes. Katrina, go ahead.
For the first one, would you have to multiply the 2 quadratics, or could you do it this way?
Before I would ever solve this, I would combine like terms. Yeah. And then if I were you, I would probably just square it because it'd be faster than trying to do use it. And there's no like x on the outside. Since there's no x on the outside, use it would be messy. I would just square it into power 1. Okay, so question. We actually just did this one, so never mind. We got that. I was saying, what if you didn't have the snazzy pictures? What if you have a different example? I think our goal today is to finish 6.2b. Which, to be honest, is the end of your 6.2 homework. Sadly. Kiddos, as a result of this and seniors being gone tomorrow, we're going to have our test next Tuesday. We're going to have our test next Tuesday. Which is good and bad. Because in a way you're having to procrastinate this homework since we're starting at the end. You could always do the homework backwards. Kiddos, you might be given something to the effect of this thingamabobbers, where they give us an enclosed region of x squared plus y squared is equal to 4. And then they say, hey, what happens if my cross sections are squares or equilateral triangles or semicircles or isosceles right triangles? Ew. Now technically, the AP, I've seen them use squares before. I've seen them use semicircles before. Equilateral and isosceles right triangles, I don't believe I've ever seen them used before. They're kind of messy, like as far as the area formula. So we might talk about those another day in like the AP review and whatnot, but let's just do squares and semicircles for right now, okay? So for right now, let's just think about squares. Since we just practiced them, let's see if we can do them again, but for a different example. Now they would have to technically tell you one other factor, they usually would. And they would say something to the effect of perpendicular. Just for sake of argument, let's say perpendicular to the y-axis. And see what happens when we slice it another way. Now, do you guys see a three-dimensional figure? And the answer should be no. But that's okay. You don't have to be able to draw these crazy shapes, kiddos. You don't have to be able to draw, where's the one with the circular? Ooh, hey, look, it's a circle. Right? You don't have to be able to say, like, hey, there's squares popping up out of it. Oh, so wait, is that what this thing's supposed to look like? And the answer is yes. Take a circle, the slices are perpendicular to the y-axis, and we can say something to the effect of, if I can actually get it oriented right, that would be what the figure would look like. Little baby squares, and then bigger, 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 etc., etc., etc. I can show my axes. There we go. Okay. So this is messy, it's rough, but you don't have to be able to show this, all right? All you have to be able to do is ask yourself the following question. Perpendicular to the y-axis, how would it slice? Right, left, or top, bottom? Right, left. Okay, so then slice it right, left. Now hold on, if there's a square that's popping up out of that, doesn't the side need to be the same? So whatever that side is needs to be mimicked by coming up, right? And then coming over. And then coming down. Now guys, is this the entire figure or is it just literally one slice? Literally one slice. So it's a representative slice that we can try to use, right? Okay, so we have our one representative slice. If we accumulate all of them, yes, we get this really snazzy picture that we don't want to draw. Okay, so, go team. We know, since it is perpendicular to the y-axis, that this is going to be in terms of dy. Because the thickness of the slice is dy, or you could memorize according to your forever card, perpendicular to the y-axis. Okay? We know our formula needs to be v equals from a y1 to a y2, a bottom bound to a top bound. We know our area formula is going to somehow be side squared because it's a square. And then we know dy. Now, you guys just answered a second ago, right minus left, right? If it's right minus left, do you guys notice what part of the square that measures, right minus left? Yeah, it's going to be the side. And don't we need these functions in terms of y? How do we get this little function in terms of y, guys?
Subtract it.
Mm-hmm. So let's do that work off to the side just for a little bit. So we'll say, okay, we need y by itself. So we're going to subtract the x squared from the 4, and then we're going to plus or minus square root, right? Oh, weird. So you solve it, and there are two functions?
Yeah.
Yeah. Why are there two functions? Don't I need one on the right? And don't I need one on the left? Right? I need one on the left and one on the right. So the left one is going to be the negative one, just using our knowledge of pre-cal. What's the one on the right going to be? So how am I going to plug into my formula down here where I need to plug in a function, or in terms of y, the side of the square? Yeah, I subtract. Who's on the right? The green one, 4 minus x squared. Who's on the left? The fuchsia, purple, that one. And if you guys notice, especially with the circle, they're going to be symmetric, meaning when you subtract one from the other, can't we just say minus a negative is a positive? So wouldn't that just be 2 square root of 4 minus x squared? Wait, what's the struggle? Dy. What was I supposed to do up here, kiddos? Was I supposed to solve for y or for x? But the nice thing is, doesn't it end up being the same if I solve for x? That doesn't always happen, just a quick warning, but in this one, since it was just x squared plus y squared, the nice thing is we're going to have the exact same equations. But we got to keep an eye out. The dx, the dy does make a difference. I can't go plugging in an equation in terms of x with dy in there. And this is going to help us because we can't finish our integral until we find our bounds, right guys? And don't our bounds need to be y, because it's everything in terms of y? Alright. So as I'm reorienting my equation to be in terms of y instead of in terms of x, what's the lowest y and the highest y for this equation? I see it going up to 2, I agree, and I see it going down to negative 2. How does the equation let us know to go from negative 2 to 2? The radius is 4, which means down 2, up 2. Why am I going to put a dot, dot, dot? You should know how to solve it, but in case you're like, how would you start? Kiddos, how would you start solving this, puppy? No, don't do you. Why am I pulling out a 4? How is that possible? Because I'm squaring the 2, that's a 4, and I'm pulling them out, and then I'm going to square the square root, right? Which is going to cancel. Good, good, good. So I'm just going to have. That's not so hard. Don't always think every integral needs a crazy use-up. Don't think every integral needs a crazy use-up. Kiddos, once again, the point of these sections is not can you learn how to solve a definite integral. It's can you practice how to solve a definite integral, and can you learn how to set up a definite integral when talking about finding volumes using known cross-sections. Okay, what's the only thing that would change? We're not going to do tons of work. What's the only thing that would change if I was to ask for the exact same scenario, except this time using semicircles? You guys are pondering, I'm showing my slice. Yeah, people are already saying, like, hey, isn't the area formula going to change? And what am I going to say? Yep. But are the bounds going to change? No. Still the same base region that I'm using, right? So still from negative 2 to 2. We're still assuming perpendicular to the y-axis, hence why I'm still showing it with dy. Except now I need What'd you say the area of a semicircle was? 1/2 pi r squared. Wait, where's the r in the picture? Is it right here? So how would I state r? Is it right minus left? Ooh, it's 1/2 right minus left. Or couldn't I say right minus 0 in this case? I don't want to go to the left, I just want to go to 0. So I could shortcut it a little bit. You could do 1/2 right minus left. That's probably a better way just for future problems for us to look at it. But you could also just do right minus 0. We could do right minus left cut in 2. Right minus left entirely would be diameter. We don't want that. So then we can end up saying that r is equal to, wasn't the right one the square root of? Wait, we did right minus left. That was 2 square root of 4 minus y squared. Divided by 2, isn't that just 1 square root of 4 minus y squared? So we have 1/2 pi, hey, look, it's the guy of the day. Anyway, times the square root of 4 minus y squared squared. Do you guys see me plugging into this area formula? We just have to think about who is the r, who is the s, who is the base, who is the height right here for each of our different slices before we plug into them. What am I going to do and say, psh, you know what to do next? Solve that definite integral. Now kiddos, I technically have some AP practice, and seniors, we're probably going to do some AP practice tomorrow on volumes of cross sections using calculators, and this is the video you need to check out for tomorrow. However, we're just going to introduce for like 1 more minute, and then you guys get to party. Is this still a volume problem? Can you guys tell? Is that a volume problem? In this volume problem, hold on, I really don't want this one. Okay, in this volume problem, can you tell what shape the slices would have? What shape would the slices have? Circular shapes, right? And don't we need to accumulate those shapes with integration? And can't we make the width or the depth be would this one be dx or dy? Slicing perpendicular to the x-axis. Dx, right? Because it's a horizontal depth. This would be a dx. What would be the area of my cross-section then? Pi r squared. The only thing that's going to change in section 6.2b, and I shouldn't say the only thing because it gets a little more complicated, but the only thing that's going to change is how do we find, it's the same one. How do we find the radius? So we do pi r squared. Here's the crazy thing is we start with area between. And depending on where we are revolving about, we're revolving a region about now? What's going to change now that we start revolving a region about? We're still going to have circular cross sections. We're still going to be using pi r squared. But how we find the r might be a little bit more complicated than what we were doing in the volumes with known cross sections, top minus bottom. Might get a little more complicated. That one was actually the hardest that you're going to see. It's called a washer. But the easier one that we're going to start with is actually, let's see if this is the right one. You need to name those 2 different things. No, those are going to be washers also. Struggle. Looks really cool though. How about this one? No. Alright, let me just show you in our notes. How about that? Do you guys see the difference between this guy, which is going to require discs, this guy, which is going to require discs, and the discs are sort of hidden back here? You guys see how this is a solid slice? Like in woodshop, you could get that like on a lathe and you could just have it solid all the way through, right? What's the difference between this one, which we're going to say needs discs, and you guys have actually a forever card down here, which is going to be forever number 48. What's the difference between this one and this one, which we're going to say needs a washer? What's the difference, guys? It's not solid. Could this hold something on the inside? Couldn't something be put in there? Yeah, right? There's hollow. Something's been cut out. Something's been removed. We have this whole minus hollow idea, kind of like a donut. You have a whole thing and then you punch out a hollow thing, right? That's why donut holes call it donut hole, because it's what's in the inside, theoretically. And then we're going to have another forever card, forever number 47, 48, 49. Kiddos, here's your homework tonight. It's not to go in the book. It's not even to do any problems. Instead, ready? It's to copy down, I'm even going to highlight it with a star. It's to copy down this page of notes, because some of you are going to want to take time on the pictures. Copy down this page of notes. It's going to be saved online. And copy down this page of notes. It's to copy down those 2 pages of notes. 6.2b, first page, second page, and then the rest, guys, it's basically examples. So what we're going to do tomorrow, my seniors, by Thursday, you need to have those 2 pages of notes totally written down with whatever detail you want, including your 2 new forever cards, 48 and 49. And then ready to basically bust through examples on Thursday. Tomorrow, what are we doing in class? AP practice, and maybe even working on the end of homework. Okay? So, seniors, watch the video tomorrow. Everybody by Thursday have these 2 pages copied in your notes. We're basically going to be practicing tomorrow, probably like a worksheet or something or others like that. Are you guys doing your book work yet? And the answer is no. People that brought food, go on up to the front. If you need a knife, there should be some in the side cupboard. The people that go up, I'm marking you down with little pies to get your bonus. Who's up there? Corey's going up. Star's going up. Sam's going up. Lauren's going up.
Was it due Tuesday or Monday?
All of you guys brought something? There were not that many objects up there.
I brought napkins.
You brought what? Yeah.
Wait, is homework due next Tuesday or
Last night.
Misty, was it due Tuesday or Monday?
And we were in this classroom.
What do you think you guys have been?
Yeah, I have 2 assignments, so I told you were Miss D. Sections. It's my practice test, and then my chapters.
Alright, 5 people, you can get 9 out of the cupboard. 5 people, go grab 9 out of the cupboard.
I need to show you something.